Okay, let's talk about Google's Willow chip, a quantum computer so powerful it's redefining the limits of computational possibility. Willow didn't just set new records, it obliterated them. It solved a problem in under 5 minutes that the fastest supercomputers on Earth would need 10 septillion years to complete. And here's the twist. Some scientists believe this quantum breakthrough might involve parallel universes where calculations unfold across multiple realities at once. So let's unpack what Willow has accomplished and why the multiverse is suddenly part of the discussion. Welcome to territory. This is your space. Google's Willow has performed a computation in under 5 minutes that would take one of today's fastest supercomputers 10 septillion years. This astonishing figure surpasses all known time scales in physics and dwarfs the universe's age by a staggering margin. Not only that, Google has also made an eyebrow-raising claim, saying that its new quantum chip may be tapping into parallel universes to achieve its results. In other words, Google claims its chip is so fast that its computations might have occurred across parallel universes, a bold assertion that has also sparked significant skepticism. So what is the science behind this bold claim? Willow is Google's latest venture into quantum computing, a chip that harnesses the strange, counterintuitive principles of quantum mechanics to tackle problems beyond the reach of classical computers. If you're familiar with quantum computing, you've likely heard of qubits. A qubit, or quantum bit, is the fundamental unit of information in quantum computing. Qubits are created by manipulating quantum particles like electrons, photons, trapped ions, superconducting circuits, or atoms. Unlike classical bits, which are strictly 0 or 1, qubits can exist in a state of superposition, meaning they can be both 0 and 1 simultaneously. Think of Schrödinger's cat, which is both alive and dead until observed. But Willow isn't just about superposition. Google's researchers have made bold claims stating that Willow can handle more complex problems with speed and efficiency orders of magnitude greater than anything we've seen before. And here's where it gets really intriguing: quantum error correction. For quantum computers to be practical, they must address errors, an issue classical computers don't face as much. The quantum states in a qubit are incredibly fragile. They are easily disrupted by heat, noise, or even cosmic rays, causing information loss. This is where quantum error correction becomes essential. Previously, the lack of error correction has been a significant obstacle to scaling quantum systems. But Google believes Willow has solved this challenge. With a new quantum error correction method, Willow could make quantum systems more reliable, enabling them to tackle complex problems and usher in a new era of computing. One of quantum computing's most exciting aspects is its ability to perform parallel computations. Thanks to superposition, qubits can exist in multiple states simultaneously, allowing quantum computers to process many possibilities at once. This could enable them to solve problems in mere moments that would take classical computers millions of years. Picture solving a giant puzzle. A classical computer would test one piece at a time, trying different combinations. A quantum computer, on the other hand, could test multiple combinations simultaneously, thanks to its parallel processing power. Now imagine taking this further. What if quantum computers didn't just process calculations in parallel but explored multiple possible outcomes simultaneously, rapidly identifying the optimal solution? That's the real breakthrough. With quantum error correction and a system like Willow, these calculations could be faster, more reliable, and more precise than ever before. Are we tapping into parallel universes? The ability to explore multiple possibilities at once resonates with the many worlds interpretation of quantum mechanics, a theory suggesting that every quantum event creates branching timelines of outcomes. While this remains speculative, Google's bold claim is drawing a lot of skepticism online. For one, the calculation Willow was designed to solve didn't have any immediate practical applications. The particular calculation in question is to produce a random distribution. German physicist Sabine Hossenfelder tweeted in response to Google's announcement, "The result of this calculation has no practical use. It's exactly the same calculation that they did in 2019 on a circa 50-qubit chip." At the time, Google made a similar claim, arguing that it had achieved quantum supremacy, or the point where quantum computers can do things that classical computers can't, regardless of whether those tasks are useful. As John Preskill, who first coined the term in 2012, wrote in a 2019 Quantum magazine column, the implications and significance of Google's breakthrough remain up for debate. However, the company is already focused on the future, aiming to scale up Willow to a level where it could prove genuinely practical. I for one am very hopeful about Willow. What about you? Let me know by commenting below. And while we are discussing parallel universes, here's a fascinating theory that is changing the way we see the universe. When looking out at the universe at the largest scales using sophisticated telescopes like this one here, one thing becomes quite evident: things are surprisingly simple and straightforward. Now, when we look inside into the universe using the Large Hadron Collider, we find that even at the tiniest scales, everything aligns with established physics. No surprises. Yet it's a strikingly orderly cosmos out there, from the colossal to the minute. Whether you're gazing at the stars or peering into the heart of matter, scientists thought that two big ideas would explain everything. One is called string theory, a massively intricate mathematical framework that, for all its flair, hasn't actually solved any major questions yet. The other is cosmic inflation, which suggests that the universe suddenly expanded faster than the speed of light for a fraction of a second after the Big Bang. But we aren't really sure what came before inflation or what powered it. However, together these two ideas suggest that the universe is super complicated when you look closely, and very chaotic from a macro perspective. Well, that does not coincide with observations. On the largest cosmic scales, the universe is both homogeneous and isotropic. This means that no matter where you are or in which direction you look, the universe appears largely the same. So it may be that the universe's apparent simplicity might just be due to the limited range of scales we can currently observe. Maybe, as we explore scales much larger or smaller, the anticipated complexity that our theories suggest may eventually come to light. Or maybe the universe really is as simple and predictable as it looks, from its grand scale to the tiniest particles. And if that is true, the clues to cracking some of the universe's biggest mysteries might already be hiding in plain sight, waiting for us to connect the dots. But what if the answer lies not in our universe but another? Haven't you ever heard of Occam's razor? The simplest explanation is probably the correct one. In the world of scientific reasoning, there's an effective principle known as Occam's razor. Let's suppose astronomers observe unexplained lights on another planet. Instead of concluding aliens are there, Occam's razor proposes to consider simpler causes first, like atmospheric conditions or natural planetary phenomena. But why bring up Occam's factor here, you ask? Because many inflation models suggest that the early universe's sudden rapid expansion should have also created long-wavelength gravitational waves, essentially ripples across spacetime. If detected, these waves would strongly confirm the inflation theory. However, despite refined searches, scientists have found no sign of these waves. And what makes it worse is that each new experiment narrows the field, ruling out more inflation models along the way. Now, inflation theory does explain some issues, but it also brings with it a lot of challenges, like what energy field actually powered inflation. Also, inflation requires the universe to have very specific initial conditions. But why were these conditions present to begin with? And then there are inflation models that suggest infinite bubble universes. Not only does this raise philosophical and scientific questions about testability, but also challenges the nature of physical reality. So ignoring Occam's razor here would be basically assuming that there are no simpler explanations. That is something Neil Turok, the Higgs Chair of Theoretical Physics at the University of Edinburgh, set out to change. Together with his colleague Lien Boyle, Turok approached a new theoretical model that could address fundamental cosmic questions without relying on traditional inflation and string theory. If we use Einstein's theory of general relativity and the known laws of physics to follow the universe backward in time, we arrive at a point where space and time shrink to a single point called the initial singularity. To make sense of the extremely dense, hot state at the beginning of the universe, theorists like Nobel laureate Roger Penrose identified a key symmetry in the laws of light and massless particles. This symmetry, called conformal symmetry, suggests that neither light nor massless particles experience the usual shrinking of space at the Big Bang, allowing them to bypass the intense conditions that otherwise affect all other forms of matter. Imagine you have a stretchy rubber sheet like a rubber band with a drawing on it. Now if you pull or squish that rubber sheet, you might change the size of the drawing, but you're not changing the shape of the things in the drawing. In a similar way, conformal symmetry implies that the universe could have a similar structure, remaining unchanged no matter how you scale it. This property could mean that rather than being shaped by an explosive event like inflation, the universe's uniformity might arise naturally from the symmetry. They propose that the initial singularity, instead of being a one-way origin, acts like a mirror in time. On one side, time flows forward, and on the other, it flows backward, like a cosmic reflection. This mirror at the Big Bang aligns with the idea that every physical process has a mirror counterpart where space, time, and particles are reversed, thus following CPT symmetry, a fundamental balance in nature. To understand CPT symmetry, imagine the universe as a grand stage where particles act out a play. In this play, charge, parity, and time govern how things behave. Now let's say that charge swaps matter with antimatter. Parity flips the scene like a mirror reflection. And time rewinds the entire sequence as if moving backward. Now CPT symmetry says that if you change all three at once, that is, flip charges, mirror everything and run time backward, the laws of physics stay perfectly unchanged. The universe doesn't break a sweat. It still plays by the same rules, like a well-rehearsed performance no matter how you rearrange it. Yet the apparent dominance of particles over antiparticles and the one-directional flow of time in our universe make it seem that CPT symmetry might be violated. The mirror universe concept, however, reinstates this symmetry by suggesting that our universe has a reversed mirror counterpart. In this mirror reality, time moves backward and antiparticles outnumber particles. This parallel universe need not be a real place but could be a mathematical construct to explain symmetry at the universe's origin. This theory also sheds light on dark matter. Neutrinos, which are light particles moving near light speed, spin in a left-handed orientation. However, heavy right-handed neutrinos, predicted to be stable, are possible dark matter candidates as they interact only through gravity. So you see, using their mirror hypothesis, Turok and Boyle calculated that these right-handed neutrinos could indeed account for dark matter. Basically, the theory suggests that if dark matter is made of heavy right-handed neutrinos, a type of neutrino that's stable and rarely interacts, then out of the three types of known light neutrinos at least one would have to have zero mass. This prediction is being tested by studying how galaxies and other cosmic structures are arranged in space. Observing how matter clumps together across the universe might reveal clues about neutrino mass, thereby helping to confirm or refute this theory about dark matter. After this, the scientists also tackled the mystery of why the universe appears flat and uniform on large scales. They explained this using the concept of entropy, which helps describe how likely certain configurations are. They discovered that a flat, rapidly expanding universe with a small positive acceleration is the most probable state. Additionally, they showed that density variation, usually linked to inflation, could actually be explained through quantum fields. However, more research is needed to ensure the new theory holds up scientifically. Picturing the Big Bang as a mirror neatly explains many features of the universe which might otherwise appear to conflict with the most basic laws of physics, wrote Turok, who published his team's findings in the journal Annals of Physics. The progress we have already made convinces me that in all likelihood there are alternatives to the standard orthodoxy which has become a straitjacket we need to break out of. While much more work is needed to support this fascinating idea, Turok suggests that even if proven wrong, it highlights the possibility of simpler explanations than those provided by the standard model. What do you guys think about the mirror universe theory? Is it here to stay? Drop in your comments below to let me know. If you like our videos, please consider becoming a member to support the channel. And as always, don't forget to subscribe to our channel, because this is your space.